Good evening all. This is a week 9 session, problem solving session for computational fluid dynamics using finite volume method. We'll get quickly started. So I will start the recording. So in last week we started discussing on unstructured meshes, and in continuation with our discussion over the last week. So when we are dealing with unstructured meshes, I'm just giving an example here. If A, B, C, D are the vertices and this is the cell centroid, 0 and 1 are the cell centroids. So we were discussing on the case of non-orthogonal and unstructured mesh. So what we mean by non-orthogonal is the line joining the two centers and the area vector of the face denoting by AF bar, and the line joining the centers is E zeta bar, and E eta bar is along the line joining the vertices B and E. Say we denote it by eta bar. Then if AF bar is parallel to E zeta bar, then we are essentially calling that an orthogonal mesh. When the area vector lies along is parallel to the line joining the cell centroids, then we are calling that as an orthogonal mesh, and otherwise we will just call it a non-orthogonal mesh. So in the last week we were discussing on how do we deal with the non-orthogonal meshes. So in all of our equations, so if we consider the general equation for a steady problem, so we have del dot gamma del phi plus S phi equals to 0, and when we try to so we'll use the standard notation where we kind of replace S phi plus SC plus SP times phi dV, we integrate along the control volume, and then we will be left out with sigma gamma grad phi f grad phi dot AF bar grad phi f gamma f summation over all the faces, plus you have a volume term SC delta V plus SP, and for phi we will assume the cell center value phi p delta V equals to 0. Now the problem we started with is how do we find out this grad phi dot f grad phi dot A for a particular face. So in the case of an orthogonal mesh, so when we started out with an orthogonal mesh, this is straightforward. So if we just consider this cell, and this is my cell 0 and this cell center for 1. So AF bar is pointing along this direction. Say this is my E zeta bar, this is my E eta bar. So how do we calculate grad phi dot A? The flux along the face, if this is my face, if this is my face, how do I calculate the flux on that particular face? We need to determine the grad phi dot AF. However, we know one thing for sure, that area vector will be normal to the face vector. So the face vector is along E eta bar and AF bar. So we know that AF bar is perpendicular to eta bar, then I can kind of express E zeta bar as A times AF bar plus B times eta bar, where A comma B are some scalars. Our objective is to estimate this A and B. Once somehow if I get the values of A and B, the next step would be grad phi dot E z bar is A times grad phi dot AF bar plus B times grad phi dot eta bar, and our objective is to get an estimate, find this value grad phi dot AF bar. So that comes out to be grad phi dot AF bar is 1 by A grad phi dot E zeta bar E z bar plus minus B by A grad phi dot eta bar. So in this expression, the known this is essentially the term we need to find, and grad phi dot E z bar is essentially grad phi evaluated along E z bar. So we know the grad phi along this direction E z bar this can be approximated by just taking phi 1 minus phi 0 by delta z, where delta z is essentially the distance between 0 and 1. And similarly, this will be along delta eta. That is something we need to find again. So similarly, we can approximate grad phi dot E eta bar, and to do that we would be needing save these points, or say we'll just give notation as say C1 and C2. Then grad phi dot E zeta bar will essentially be phi at C2 minus phi at C1 by delta eta. But however, to do this thing we need to know the values of phi C2 and phi C1, but these are essentially the values of the phi evaluated at C1 and C2. But from our original definition, we defined phi to be only defined at the cell centroids. Like our data structure is phi is only stored at cell centroids. And not at vertices. So because of this, we will not be able to directly get the value of grad phi dot E eta bar. So instead what we do is something we call a deferred correction approach, in where we try to estimate this in a reverse way. So we try to estimate grad phi from the previous iteration value and use that grad phi to evaluate this coefficient of the secondary gradient. So our objective is to estimate grad phi dot AF at current time step is something that I want at current time step. So what do? Grad phi dot E zeta bar is something that I know. Phi 1 and phi 0 is something that I will be finding in the current time step or current iteration value. So it will be 1 by A phi 1 minus phi 0. So from the by delta z. So the term A times delta z will go into my summation sigma A and B and AP term. So this coefficient 1 by A delta z will essentially go into my AP and A and B terms. And the second term, what I do is this entire term is something that I cannot evaluate because I do not have the values of phi stored at the cell vertices. So instead what I will do is, again I will consider grad phi dot AF. So essentially what I will do is minus B by A grad phi dot E eta is something that I know, but grad phi is something that I do not know at the current iteration value, but I will know at the previous iteration value. So I will just use the previous iteration value of the grad phi. So in that way I will be able to estimate at the current the flux at the current iteration value in terms of the cell centroid values, and then previous gradient from the previous iteration value, and this will essentially go into your B term. So now the question is, what is the value of A and B in equation number 1? So we have E zeta bar essentially given as A times AF bar plus B times eta bar. So from this it is straightforward. One thing is clear, that AF bar and E eta bar are perpendicular to each other, because E eta bar is essentially the line joint, is essentially the face, and AF bar is normal to the face, it's a face normal. So both are perpendicular to each other. So if I do a dot product with AF bar dot E zeta bar, E psi bar will essentially give you A times AF dot AF plus B times AF dot E eta bar, and this essentially goes to 0 since AF bar is perpendicular to E eta bar. So what this gives me is A equals AF bar times E zeta bar by AF bar times AF bar, and similarly I can do a dot product with E eta bar. So E eta bar dot E psi bar is A times E eta bar dot AF bar plus B times E eta bar dot E eta bar, and however this particular thing is again 0. So from this we'll get a value of B equals E psi dot E eta. It's like it doesn't matter since for a dot product A dot B is essentially equal to B dot A by E eta bar dot E eta bar. So now that I know the values of A and B, so if I substitute back in my original equation, so my flux grad phi dot AF is essentially 1 by A. 1 by A is AF dot AF by AF dot E psi bar times phi 1 minus phi 0 by delta psi. And then I have minus B by A is essentially minus E psi bar dot E eta bar by E eta bar dot E eta bar into AF dot AF by AF dot E zeta times you have grad phi dot E eta bar. So now using this expression I will be able to evaluate all of them. So the only question right now is how do I get the value of grad phi. So in last week we discussed grad phi can essentially be calculated in two ways. Either we use a gradient method or essentially least squares method. So we tried solving using gradient method. So how do we start with that is we will see an example of that now, and we discussed the least squares method in the last week. So this week we will discuss on the gradient method. We'll start with question number 1. So C is this polygonal element here. So if my face is, so C is the polygonal cell centroid of this particular polygon shown here, and then say let me put some names to this. So I'll denote small lowercase letters, or maybe we'll A, B, C, D and E. All the lowercase letters are the vertices of the particular element, and then we have cell centroid as capital C and the neighboring cell centroid as F. So in our notation, if this is cell 0, this will be cell 1. So the question asks you essentially the value of phi, the analytical value of phi is already given by this following expression: phi is equals x square plus y square plus x square y square, and the total volume of the cell is also specified. So it asks you to find the gradient at C both numerically and analytically. So how do we start with such a problem? So let's take this problem on. So we have something like this: A, B, C, D and E, and then we also have this as cell centroid C, and this is cell centroid F, and phi is already given as x square plus y square plus x square y square. The question now is asks you in the first part is to calculate grad phi at C. So analytically it is straightforward. So first step is to calculate grad phi, that essentially is del phi del x I hat plus del phi del y j hat. So this gives me 2x plus 2xy square I hat plus 2y plus 2y square j hat. Now at point C, we know the coordinates of point C are given. The coordinates of point C are given as 1.75 comma 2. So it's 1.75 comma 2. If you substitute this in this, you will get the value of grad phi. So at C, this is analytical way of doing it. So the next part essentially asks you to find the gradient numerically. So how do we go ahead? So we were discussing on the gradient method. So by gradient method, what we mean is we use a Green theorem. So what it says is grad phi C evaluated at C times volume of the cell is essentially equals summation of phi evaluated over all the faces times area of the face. This should include all the surrounding faces of that particular cell. So if these are my faces, F1, F2, 3, 4 and 5. So I'll just put in this annotation here. So for all the faces phi Fi, AFI, where I is going from 1 to 5. So here, since we already know the analytical form of the phi, so we can just calculate phi f as use that expression x square plus y square plus x square y square evaluated at face center. So all the vertices are already given to us. So A is given as 3 point. So our first step is to essentially calculate the face centroids. Once we get the face centroid value, we will take the value of phi at the face center and then multiply by area of it. So I'll just outline the steps here. So the first step is essentially determine the face centroids. We know all the vertices, so we will determine the face centroids. From the vertex coordinates. The next step is essentially once we get the face centroids, we need to find the area of the face. Area of the face is essentially the length. In this particular case, we are essentially considering unit width along the other direction, z direction. So we will calculate the length of the face again from the vertex coordinates. So this will essentially give you phi f I, and this will essentially give you AFI. So you can just do a summation of it, and then once you get the values of this, from there you already know the volume of the cell. So grad phi C is essentially given by sigma of phi fi and AFI by volume of the cell. The only problem here that we would be facing here is how do you determine the direction of AFI. So the question is, so in this particular simple case, we know the values of this. Say this one of these points is x1 y1 and the other point is x2 y2, and this is my face. this is my face centroid, say xcyc. xcyc is straightforward. xcyc will essentially x1 plus x2 by 2, it's just a midpoint of it, and y1 plus y2 by 2. So now we have an area vector AFI. So how will I calculate AFI? One thing we know for sure is AFI is perpendicular to, if this direction as per our notation is E eta bar, so it's perpendicular to E eta bar. E eta bar is straightforward to calculate. So E eta bar is essentially x2 minus x1 I hat plus y2 minus y1 j hat. So how will I know the AFI bar? So in 2D it is straightforward again. So we just need a perpendicular vector to this. So that would be y2 minus y1 I hat minus x2 minus x1 j hat. However, there is just a small thing to note is this could be either plus or minus. So essentially our E eta bar is along the specific direction, and your AF could either be pointing in this way or it could point the other way. Both of them are actually perpendicular to E eta bar. So how do we essentially determine, so either this is option 1, this is option 2, how do you know which of these is to take? So plus would give you one direction, minus would give you the other direction. And what we need is if our cell center is towards side 2, so how do we choose cell is essentially how do we choose which of these area vectors should I take for a given value of in my gradient calculation is essentially depends on where your cell centroid lies. So if your focus is on cell 0, so if this is my cell 0 and this is my cell 1, and let's call these regions as instead of 1 and 2, say region A and region B. So when we are doing for cell 0, I want my outward normal. So which means I should take the corresponding vector which will be in region A, and when I am at cell 1 it will be in the other way direction. So outward normal will be along the B direction. So the choice of the sign plus or minus should depend on which cell I am currently considering. So for a given phase, for a given cell, once we know which cell we are working on, so in this particular problem we are working on cell C. So for the cell C, when I am considering this phase, the outward normal will be along this. So I should take my area vector pointing in the direction away from C. So how do I do that? So how do I determine the sign of this? So how do I check the sign of this? Is one simple step is to first you calculate the value of AF bar. You just take say delta y I cap minus delta x j cap, where delta y is essentially y2 minus y1, and so I am just calling this as delta y and this as delta x. We just assume a sign. Here we are just assuming, the first step is we assume some sign for AF bar. So we assume a positive sign here, and then we will check whether it is pointing inwards or outwards of the given center. So how do we know whether it is pointing or inwards or outwards? Is essentially do a dot product. So as we know, like dot product will essentially be positive if they are in the same direction, and it will be negative if they are in the opposite direction. But for that I need to have a reference vector. So which one of these would be my reference vector? So if this is my cell centroid and this is my face, and if this is my face centroid and my area vector is pointing in some direction, I want my area vector to point in this direction, but I do not know whether it is actually pointing in the direction. So it could be either pointing in the direction or it could be pointing in the other way. So it could be either this way or the other way. So in order to determine that, what I do is I do a dot product with the line joining the cell centroid and the face centroid. So this particular line is say I am calling d bar, d c times f1, since in our particular problem this is denoted by c, and this is the phase center for phase 1. If it is phase center for phase 1, then DCF1 is essentially the vector joining the cell centroid with the phase centroid of phase F1. And then we have calculated AF bar as delta y I cap minus delta x j hat. So when I do a dot product with DCF bar, DCF1 bar, so you can see there are two possible cases. So it could either be case A or it could be case B, where you have so one thing is for sure that theta A plus theta P will be essentially 180 pi or 180 degrees. So which means when you do the dot product, you either get a positive value or a negative value. So if it is positive value, then it should be pointing in a direction very close to DCF1 bar. So which means it will be pointing in the direction away from the cell centroid DCF1. And if this turns out to be positive, it means I am pointing along the outward normal. If it turns out to be negative, then it means for the cell 0 I am pointing my AF bar in the opposite direction, that is in the direction P. So this is case A. So what do I do in that case? You just multiply with a minus. So when you find out that your dot product with DCF bar is negative, then you just multiply that multiplied by the area with a -1, so that your area vector will always be pointing in the outward normal direction. So if I determine the area vector in this particular way, I use this area vector in my above equation, in this equation, and then I will calculate my grad phi. So this grad phi is for cell 0, that is for cell C. Now this is how you go ahead for a numerical way of calculating it. See, similarly the question is the next part of the question asks you to find the value at grad phi at the next phase, next cell centroid, that is at point F. So that is again straightforward. So you know the grad phi analytical expression. So we know the phi, from there we calculated grad phi, and you just substitute the point F, that is 4.25 and 3.5. Once we substitute that, we will be getting the value, analytical value of grad phi. The third part of the question asks you to interpolate between the numerical value of grad phi at C and analytical value of grad phi at F to find an approximate value of grad phi at phi1. So as we were discussing, so why are we doing all of this? Why are we trying to do all of this is essentially because we need grad phi dot AF, grad phi dot A on the face. But from the above method, what we get is essentially we get either grad phi C and grad phi F. So we just get the gradients at cell centroids. Once I get the gradient at the cell centroid, so how do I calculate the gradient at the phase centroid? This is essentially the gradient at the phase centroid. So we could use several interpolations. The simplest one would be, you know, this is 0, and so you have a phase centroid. This is my phase. Say here we are using a different notion. So this is my point C, this is my point F, and say this is my phase center. Little f is my phase center. You calculate the distance between these two. Say that comes out to be dc little f, and distance between these two as the capital F little f. So we would just use the lever rule where grad phi at phi is essentially a weight combination of these two. So it goes something like dff times grad phi at C plus dcf grad phi at F So do I know these values, DFF and DCF? We know the coordinates of all these points. We know the coordinates of C, coordinates of little f, and coordinates of capital F. So once we know the coordinates, we can actually calculate this as the Euclidean distance. So from this we can actually get this one, or a simpler way would be to just take equal weightage to both of the gradients and just take a mean value of this. So if you are dealing with some kind of a uniform kind of a mesh where you have both of these to be equal, so both these distances to be equal, in that particular case you can just take the mean value. So the present problem attempts to try this in two different ways. So grad phi f is essentially calculated analytically, but grad phi c is can be calculated analytically, since we know the analytical expression for phi, and then we can calculate it in a numerical way. So what we try to do in this problem is essentially compare these two and see if, how the error is. That is essentially the third part of the question. And the fourth part is essentially to compute the secondary gradient along the face f1. The fourth part essentially asks you to calculate the secondary gradient along face f1. So if this is a face centroid and you have cell centroid as capital C and capital F, so as we have seen, the secondary gradient is essentially some constant. So like as we have followed, we just call b by a as some constant, or if you write the expression, times like we were saying, it will be grad phi dot eta cap. So the first step is essentially we know the coordinates of these 2 points. So this is a and b. So once we know the coordinates of a and b, we can directly calculate the eta cap. So this is xa xp, sorry, xa ya, and if this is xp yp. So eta cap is straightforward. So that will essentially give you yb minus ya j hat plus xp minus xa I hat by the distance of the between the points a and b. So that will give you eta cap, and E zeta cap is again straightforward. So you know the coordinates of C and you know the coordinates of point F. So this should directly give you the EC hat between C and F. So I am just writing F minus C. So this should give you E zeta cap, and AF bar, like we have discussed so AF bar is essentially YB minus YA times I hat minus XB minus XA J hat. However, the sign before it can be either plus or minus. That depends on which cell you are focusing on. So if you are focusing on cell C, say if this is my focus, this is my current cell, and F is on the other side. So how do I know to say if it should be plus or minus? We start with a vector pointing along CF1. So I will calculate DCF1. So that essentially is F1 minus C. So when I am writing F1 minus C, what I mean is you just take the XF1 minus XC I hat plus YF1 minus YC J hat. So you calculate DCF1, and we first calculate AF bar. We first assume that AF bar is positive if we consider it in this way, and then what we do is just take a dot product of DCF1 dot AF. So now this can either be positive or negative. So if it is positive, in that particular case, whatever we have assumed is correct, that it is pointing outwards. So the idea is when you have DCF1 pointing in this direction and AF bar is pointing in a direction as an outward normal, then you have this as an acute angle, and then your dot product will essentially be positive. So you will use the same one. And in the other case, when you have, if this particular formula you have assumed is coming in an opposite direction, then when you do the dot product with BCF1 bar, since the angle is greater than 90, it would turn out to be negative, and in that case you multiply your with a -1 with whatever you have assumed in this step. So if this is equation 3, you multiply -1 in equation 3, and then you get your new AF bar, and you use this AF bar in this original secondary gradient expression. So now you have AF bar, E zeta and E eta cap. So you can calculate the secondary gradient only if you know the grad phi. It's like we have already calculated grad phi previously, which we will be using here. So this will give you the secondary gradient. Yeah, we'll quickly go through the implementation of this, and then we'll come back to the next question. So I'm just defined a new class vec to essentially store the points. It just has some additional functions so that it will be easy to do your some of the algebra, just to make some of the algebra a little easy while you code. And so essentially I have given all the points A, B, C, D, E and F. Those are my vertices of the given cell. Capital C and capital F are the cell centroids for the current cell and the neighboring cell. And I've just given defined the faces in a way where each face is essentially composed of two vertices, and in addition to that I am also giving a third argument. The third argument is essentially the cell centroid I am focusing on. So if I want to focus for cell with the cell centroid capital C, I am just passing capital C, so that your area vector will be chosen in a way that is outward normal for that particular cell. So we'll see how this is implemented. The analytical gradient is straightforward, so you just calculate you have the analytical expression for phi, and from there you will get the grad phi term, and then substitute the coordinates of C in that, which will give you the analytical gradient. And for the numerical gradient, the first step is if you are using the green method, so gradient method, the first step is essentially to calculate the fluxes, or you calculate the value of phi on all the face centroids. So F1 through F5 are my faces, and each of it has a parameter called centroid, which is the face centroid. So what I have done is calculate the phi at the face centroid, and I have stored it in some variable. So once you have all the velocities of once you have all the phis on the face centers, the next step is to multiply with the corresponding areas. And then once you have all the areas, you just do a summation of sigma phi times A divided by volume of the cell. That should give you the numerical value of it. And for the interpolation part, now that this gradient will essentially give you gradients at the cell centroid. So now I have two cell centroids for a given face, like for every face is surrounded by two cell centroids. So I know the value of grad phi at C, point C and point F. Now that I know these two values, I need to do some interpolation to get the value at the face. So for that interpolation, I am just using kind of a linear one, where you calculate the distance from the cell centroid to the face centroid, say C to F1 and F1 to F, and then take a weighted average of this to get the value of grad phi at the at the face centroid. That would be my analytical value. And similarly, I can that would be my numerical value, and then I know the value of phi directly at the cell centroid, and I know the analytical expression for grad phi. If I just substitute that here, so I will get an analytical value. The third part is essentially to try to calculate your secondary gradient. Like I have seen, to calculate the secondary gradient, I need two vectors, E z bar. E z bar is essentially F minus C. As we have seen, it should be pointing away from the center of the cell of our interest. And DCF is essentially the distance of that particular distance between the two cell centroids. So E1 essentially stores the unit vector pointing along C and F. E2 bar is essentially, E2 here is essentially E eta bar that we were discussing previously, and that is a unit vector along this direction. So I just put some factor here, that is area dot area, that is AF dot AF by AF dot AF into E eta dot E2 is essentially E eta and E1 is E psi. So I just do a dot product of it. So in case of an orthogonal mesh, this particular term will drop to 0. So we don't have a secondary gradient. And then we have AF dot EC. So once I get the factor, secondary gradient, next step is essentially you multiply this factor with del phi del eta. So since we do not know del phi del eta, we were essentially taking it as grad phi dot E eta. So I know the grad phi. So I have grad phi evaluated in two different ways, like I can do it in analytical way and then in a numerical way, and then I just compare both of these. So before actually seeing this, we will just see a little of this, how do I evaluate these areas. So to evaluate the area, like we have seen, the first step is essentially area has delta y I cap and a minus delta x j cap, and to determine the sign, what we are doing is you take the face centroid. This centroid is the particular face. For that particular face, minus r is your reference point. So when you are on cell 0, you take the cell centroid of that particular cell as a reference. So that centroid minus r will always be pointing in a direction away from the center. So it will be always pointing in a direction that is that will give an acute angle when you do a dot product with your area vector. So I just do a dot product with area vector, and if it is negative, I just change the sign of my area vector. So this will ensure that your area vector is always outward normal for that particular cell. So if we just quickly run this. So analytical gradient and C, as we have seen, it is you just have the expression for grad phi. Grad phi is essentially 2x plus 2xy square and 2y plus 2yx square. So if you just substitute that, you will get an expression for this. And the next step is essentially I calculated the face value of it at all the face centroids, and I updated the area vectors. The numerical gradient at C is essentially summation of phi times A divided by volume of the cell. So the point here is to compare this numerical gradient at C with the analytical gradient. Okay, the first step and this step. So if you compare this with the first line, so they are kind of close to each other. So this is just a first step. In the numerical approximation, the one we were doing is essentially we are doing an approximation of first order. So they may not be exactly equal, but they are kind of close to each other, that you can see. And for f at capital F is ideally we should be doing it numerically, but to do that we need to know all the neighboring points for that particular cell, which we do not have. So we directly use the analytical expression of phi, and then we obtain the analytical gradient at point F. And similarly, using this numerical gradient at C and F, we can calculate the numerical gradient of face centroid. So just by taking a weighted average of these two. So if I use, so if you just see the difference between these two, and the final part is essentially to calculate the secondary gradient. So I just compare the analytical value with the numerical approximation that we were doing. So they are again quite close to each other. I think this concludes our first question. So if there are any doubts, or we can go to the next question. I think we can go to the next question. Yeah, the second question is again a straightforward steady state heat conduction without any source terms. The only difference is now we are dealing with a non-orthogonal mesh. So since it is a non-orthogonal mesh, we will be having the secondary gradient terms. So this is a Dirichlet condition, and then this is a Neumann condition. and then I have a digital condition on the last boundary. So the equation is again straightforward, del square t equals to 0. So all the steps are very similar to what we do in a study in a normal mesh. So I'll just focus on how do we actually try to solve this. So the only difference in, say, when we try to actually implement it in a code, the things we need to care about is, first is, I'll just go through the code of this, then maybe we'll see how originating it. So I've just defined few of these classes. So each point, a point is essentially it's a data structure to store each of your vertices and with some of the additional operations so that you can easily calculate your centroids and other stuff. A face essentially has some important points. So we are focusing on face centered data structures. So face essentially stores an area. So this is just the magnitude of the area. And then we have an en cap, e eta. En is essentially e eta. So if you have a face, it essentially have two vertices v1 and v2. And e eta is pointing along this direction. So e eta is essentially v2 minus v1. If I just put this so that it will be a normal vector, and capital A is this. But how do I fix the direction? Like we have seen, to fix this direction I need to give a reference point. So in order to do that, what we do is we maintain another connectivity matrix. So what that matrix stores is, for every cell it gives to all the neighboring faces, and every face it will also store the neighboring cells. So for every face it will store two neighboring cell coordinates. Like I'm just giving this as the local coordinates, so 0 and 1, and then you also store the global indices for these cells. So this will be my cell 0 and cell 1. So this A bar is always stored in such a way that it will be outward normal to cell 0. So the direction of A is always fixed. So for a given face, cell 0 is the reference cell always. So when we try to calculate the A and B term, so since this term, I will essentially go to the A and B term, and then this is important in A and B as well as your secondary gradient term. So when we are dealing with the secondary gradient, how do we decide? So if you are on cell 0, you take the positive value of it, and then when you are on cell 1, it will be just opposite of it, so you just take a negative value of the same value. So we calculate only once and then use it twice in when we write the cell equation. So we will see that later. So grad is essentially the grad phi f. So this is essentially grad phi evaluated at f, and E1 is essentially the C1 minus C0, which we will again, like, since for every cell we fixed what is for every phase we fixed what is cell 0 and cell 1, E1 will essentially correspond to C1 minus C0. I know C1 and C0, so I just get the value of E1. So to get a unit vector, I just so here you have magnitude of V2 minus V1 to just get a unit vectors of E1 and En. Centroid is again for the, you just take V1 plus V2 by 2, and A and B. So A and B is essentially the term that will go into your cell equations. So I am storing them in the face. So for every face has a given value of A and B. So what this A and B is essentially the flux on that particular face divided by phi1 minus phi0. This is essentially my A and B for that particular face. Now when I am storing this, I am not differentiating between any interior faces or the boundary faces, because this term will be there for all of them. The only difference will be when you actually do populate this into your cell equations. So only when you try to write your cell equations, you include only the terms that are for the interior cells and treat the boundary elements separately. So we will see that later. So for now, A and B is essentially stores this particular coefficient for each of the face, and secondary gradient is also associated with a face, so I will store that in this face. Index is the global index of the face. So what we were trying to do is all the faces we will store in a single array. All the faces will be stored as a single array, all the cells will be stored as a single array, and vertices also will be stored as an array. So each of these cell will have a subarray indicating what faces are connected to that cells. So each of these will again link to the particular index in the face. and each vertex will have each face will again have some vertices. Each vertex essentially face will have the indices of the vertices, and cells will have indices of the face, and vertices will actually store the coordinate points, the actual coordinates of the vertices in terms of the x and y coordinates. So that is implementation of face. It also has a phi term, that is essentially the value of phi evaluated on the face. This will essentially be used for calculation of secondary gradient. And inside a cell we have all the list of faces. So here it just stores the face indices. So each cell will store the indices, global indices of the faces of this particular array, and then we have a centroid and a gradient term. So this gradient is gradient evaluated at the cell centroid, and you have a volume of that particular cell. Index is the global index of the cell, and phi, so each cell will have a phi there. So this is our unknown that we will be trying to solve. Mesh is again an object that will store your all the cells faces and your vertices. So here we have different types of conditions. So this is the number of cells, faces, points, and then boundary. So we have to treat boundaries different from them. So I've just put another variable for that, and you define your cells and faces and different kinds of boundary conditions. So how are we trying to give the boundary conditions is, say you have a domain, or maybe we will take the current question. So if I just label the faces as something like 1, 6, 7. So I have total 12 faces. Out of these 12 faces, the first 8 faces are my boundary faces. So when I am giving these type of boundary conditions, I will try to give all the 4 different kinds of boundary conditions. So in our particular case, the first 2 have a boundary condition of Dirichlet condition. So I will just put 2020, the value of Dirichlet boundary condition, and second and third phase do not have the Dirichlet condition, so I will just put a 0 there. The fourth and fifth again do not have anything, so I just put 0, 0, and the sixth and seventh will essentially be the other boundary the Dirichlet condition. So similarly the Neumann condition is there everywhere, so I just put zeros here. So if you have a given flux, you just put the flux there. Even when you have a given convective condition, you just put the value of, so for a convective condition you need to know both the heat transfer coefficient as well as your ambient value of that phi. So both of them will again be given in terms of an array, where this array length will essentially determine the faces that are having that are treated as boundaries. So the length of this array is essentially the number of your boundary vertices. So now that I am defining in this way, now I need another connectivity matrix to essentially link between the global faces as well as the boundary faces. So points are essentially the vertices of all of them. So these are my connectivity matrices. So face to cell essentially tries to connect a global face. So like we have seen, so if we have a given face, a global index for this face, and then you have a local cell numbers 0 and 1. So for every face we have 2 cell neighbors. So if and when we are doing our calculations, what we would be needing is, say I want to calculate phi f. If I want to calculate the phi at this point, say if this point is f, maybe if I just come up with an approximation as phi 1 plus phi 0 by 2, then I need to know the value of phi 0 and phi 1. But 0 and 1 are the local indices, but I would be needing the global indices. So I should store some connectivity matrix which tells me what this 0 corresponds to in the global cell index and what this 1 corresponds to in the global cell index. So that is essentially this face to cell. Face to cell will essentially link a global face. So if you give a global face and a local cell, it will give you the global cell index. Cell to face is what you will be needing in the reverse way. So if instead you are going in an opposite way, where say you are given a cell and you know you need to calculate the gradient or some other thing on the face, then if you know the global cell and global face values, you need to find the local face value. We will see where this will be useful in short time. So maybe when it comes, then it will be appropriate to discuss on that. And face to boundary is essentially this indices between say the boundary conditions are again will be given only for the boundaries, only for the boundary faces and not for every other face. So we need to know out of the total global face indices, which one of them are actually the boundary faces. So you have a face, so these are my faces, so you have a global indices, all of them will not be your boundary faces, so you need to kind of select which one of them are boundary faces. So these are only given in my boundary matrix. Boundary matrix will essentially be 0, 1. So now I need a mapping between my boundaries and the global face indices. That is something that is being stored in the global face to boundary. So these three are essentially your connectivity matrices that need to be given by the user, or you can kind of do some algorithm to actually find those things. And AP and B0 are essentially the variables that I will be using my cell equation. So like our cell equations are again similar. So you have AP times VP is sigma A and B phi and B, A and B F for all the neighboring points, and or I'll just write A and B. Plus I'm just using B0 here. And the next important point is to store another connectivity matrix, which is the neighbors. So this neighbors is essentially telling you which cells are connected to which other cells. So it is a cell to cell connectivity. So in our case, say if I give instead of faces, if these are my cells, so I would be I should know which are the corresponding cells. So for cell 0, the neighbors are 1 and 3, cell 1, 0 and 2, 1 and 3, 0 and 2. So this is essentially the information that will be stored in your neighbors matrix. These are just some helper functions. So add points is so like since our course is essentially doesn't deal with how to generate a mesh and all of that. So what I was trying to do is given a mesh, how do we go and solve our system of like given a mesh of with the vertices and all your faces, the connectivity matrices, given all of these things, how do you go ahead and solve your like make your discrete equations and then solve them. That is the main objective of this course. So I'm just using a helper function add points to essentially give your all vertices, and then the next step is once you give the vertices, you also need to define your faces. So I'm just updating the area centroids directly from these faces. You know area centroid, and then you can calculate E eta right from there. So this is quite straightforward. And then boundaries is something that we have to specify, user needs to specify. So this is another helper function to take in all the boundary function, all the boundary values. Again, cells also need to be specified by the user. So if you just give the faces, and then we need to connect which faces are connected to each other to form a cell, that information will be stored here. So it has two, that is just to kind of make it easy to calculate cell centroids. So this the first argument essentially takes in faces, the second argument essentially takes in as vertices. So what I meant by this is say you have a cell 0. So you can specify it in two ways. You can either give me the vertices, the coordinates of all these vertices. Alternatively, you can tell me what faces it is connected to. If and faces, again I know each face, I know what the vertices are there, so from there I would be able to store myself. So you can do it in either of these two ways. I am using both of these arguments to essentially store the cells. The cells are actually stored in the data structure we are using is it just stores the face indices, it doesn't store the vertices. I am just taking the vertices argument as well to calculate the volume of the cell. It's like the volume of the cell is much easier to calculate when you know the coordinates of the points in a known fashion. This again becomes important when you are giving input. So the formula ensures that like it started out with the assumption that your vertices are given in anti-clockwise direction. So you should start from A, B, C and D. So it should go in only in this particular order so that your volume will be calculated appropriately. So if it is a clockwise, then you have to multiply with a -1, but if the coordinates are given as say A, C, B and D, then the formula wouldn't give you the correct value of the cell. So that should be something that should be taken care of. But when you are using some automatically generated mesh, this is automatically taken care of, so you don't have to worry about that. But in this particular code that I am showing you, that is not implemented. So cell centroid is again straightforward, so you just take the face and just add all the vertices divided by the number of vertices will give you the cell centroid. Volume is something you can calculate from the formula, like if you have the volume of a cell is essentially given as say if it can be any polygon. So if you have a polygon, be it regular, non-regular, whatever, and you have the coordinate points as and say this is x and y n, your volume is essentially given by x1 y2 minus x2 y1. Okay, and just put an absolute so that I have written it in a clockwise direction, so it will turn out to be negative, but if you just put an absolute before it, so it's x1 y2 minus x2 y1 plus x2 y3 minus x3 y2 and so on. So you have xn minus 1 yn minus xn yn minus 1, and then you have the last one will correspond to xn y1. So like this will be, okay, maybe I should write yn minus 1 and this is my last one, xn yn. So we will circle back to the original one, so you will have xn y1 minus x1 yn. So this will give you the volume of the cell. So you have updated the volume and cell centroid, and index is just a global index that you are showing. So once you have added the cells, the next step, this is another helper function to actually update your connectivity matrices, which can actually be given by the user himself, or if you want to update them, that is again quite straightforward. So what I am doing is I am just iterating through all the cells and then see which of the cells is connected to what all faces. That way I will update my cell to face, and then I will go iterate through all the faces, and then I will see which of these are boundaries, and then that will update my face to boundary. Similar way I will update through all other faces and see which of these cells are the neighboring cells, and then I'll update my third matrix. So this is just some helper function, or you can be away with it and then you can write your own connectivity matrix. The next important part is how do you update my phase coefficients. Like we have seen in our phase-based data structure, we will store all the fluxes only at the faces, and when we are writing the cell equations, we will use the appropriate sign for it. So to calculate a phase coefficient, I will need two vectors. So E1 and E1 is essentially E psi, and E2 is phase. So this is my phase. From my phase to cell matrix, I have fixed what is cell 0 and what is cell 1. So this is my E1 here, and E2 is phase to cell centroid. So if this is my phase centroid, so this is A2. Why am I doing E2 is essentially to determine what should be the sign of my area vector. So when I do a dot product with E2 bar with the AF bar, if it turns out to be positive, then it is correct, otherwise I will just multiply it with a minus 1. So I will just use a sign of this dot product, and for that purpose I need to store this E2. DE1, DE2 are just the distances, and factor is that coefficient, so you will see that. So C1 and C2 are essentially the cell centroid, so this I am calling C0 and C1. So what I do, I will just iterate over the faces, and for each face, the only difference is when you have a boundary cell, in case of a boundary cell you won't be having C1. So if this is a boundary, if this face turns out to be a boundary face, then in that particular case you will just have C0 and you don't have C1. So what I will be doing is, instead of considering C1, I will consider the phase centroid as my C1. So I am just considering phase centroid as C1. That would be the only difference, otherwise everything else should be similar. So that is taken care in this particular case. So phase to cell I1 is essentially minus, so I am just giving, so phase to cell essentially stores the global indices of the cell. So given a global index of the phase and a cell centroid 0 or 1, so essentially it can be either 0 or 1, it will give you the global index of that particular cell. So if it is minus 1, it means there is no cell in the other direction, which means it is a boundary cell. In that case, I will just consider C1 to be my phase centroid. So now that I know cell 1 and cell 2, I will just, E1 is essentially C1 minus C0, that will give me the direction of E1, and I just calculate the unit vector. And E2, like we have seen, it between the cell centroid and cell 0, and I calculated the unit vector of that. So if the dot product turns out to be negative, I just replace the area with a negative one. And factor, this is essentially our to consider for this non-orthogonality, where you have this is af dot af by af dot ec hat. So this is that particular term, and your a and b is essentially k times this particular factor. That will give you your a and b term. So if you recollect, so this will be multiplied by phi1 minus phi0, which will essentially go into your cell equations. So we will just store this particular coefficient in a and b, and then I'll update my f. So this I'll iterate through all the phases, and I will update all the values of a and b for each and every phase. Once I have done for all the phases, the next step is to write my cell equations. So that is, so this part is essentially for updating the phase topology, as the name of the function says. The next is essentially to update for the to write the equations for the cell. So first I update the values of phase coefficients. Next I need to calculate the gradients, which I am stepping right now for. Like this is useful when you have a non-orthogonal mesh. So we'll come to gradients part later. Say suppose we already know the gradients. In that particular case, how do we calculate the coefficients? Is you need to separate differentiate between the boundary and the non-boundary cells. So okay, this is only for boundaries. Okay, so this particular condition is if boundary index is -1, implies that is a boundary, like we have seen boundary index phase to boundary stores the global indices of phases for the corresponding boundary points. So if it is -1, it means that particular phase is an interior phase, so it doesn't have any mapping to boundary. So if that is not equal to -1, which implies it is a boundary phase. For the boundary phase, like we have seen, we can have different boundary conditions. So this is for a mixed condition, and for a Neumann condition you just need to add the term to the B0. And if you have a Dirichlet condition, you need to take care of both the A0 term, like previously when we were discussing on steady state problems. So we were seeing, so we have AP, A and B and B terms. A and B will always be 0 for a boundary phase. So whenever you try for a boundary, that we either know that value or somehow estimate that value, so that A and B term turns out to be 0. In case of Dirichlet condition, we will have a contribution to both AP and B. So AP will essentially have some contribution like k times 2k by delta x. We used to get some terms like this getting added to the AP term, and then in the B term you will have a similar A and B times phi b is essentially the boundary value. This is for a Dirichlet condition. So in Dirichlet you will have an increment to both AP and B. Now when you have a Neumann, when a given flux, for a Neumann your flux doesn't contribute to your AP term, so you don't have any terms here. But in the B you will have an addition of the whatever flux that is given. And for mixed condition, we will have an addition both to AP and B. So the term that is contributing to AP will have some equivalent conductivity that will be adding to AP term, and to the B term will have some equivalent conductivity times phi ampere. So this will be adding to your B term. So first I have updated the B terms, and only for a Dirichlet condition I will be updating my AP term. Okay, for Dirichlet and mixed conditions, for both of this I will be updating the AP term. If it is not a boundary phase, then it is straightforward. I have already taken care of secondary gradient here. So if it is not a boundary one, if it is only the interior cells, for the interior cells B term comes from two things. So either it should come from secondary gradients if it is a non-orthogonal mesh, or it should come from source terms. And this will be there, source terms will be there even if it is boundary or not. The same is the case for secondary gradients. Even if it is a boundary or not, the term should be adding up. So I have just taken it out of the if condition, so that this value adds up even if it is a boundary or not. And AP will also have this SP term that is independent of whether it is a boundary or not. If it is not a boundary, just take the value of sigma A and B. So AP is essentially, I am just doing a plus equal to, so that this AP is essentially equal to sigma A and B for all the interior cells. I have already updated for the boundary cells in the first part of this. Now it will have an additional terms from the interior cells as well. Now once I run this particular function, now I will have all the values of AP and B updated. We'll come to update gradients later. So that is only for non-orthogonal meshes. The next step is to you just initialize your mesh with some initial condition, and with your update your connectivity matrices and all of that. That is straightforward. Gauss ideal is again the same as we have done previously. The only difference here is in your summation term. So your summation term now has sigma a and b times phi and b. Previously we were used to do I plus 1 j plus 1, but in an unstructured mesh you wouldn't have something like that. So you need to use your connectivity matrix, that is your neighbors. So neighbor of I and j will essentially give you for cell 0 what so say if you have a triangular mesh and this is my cell 0, have something like this. These are my 1 2 3. So neighbor of 0, again each of these will have some local coordinates. So if this is 0 1 2, so of 0 will give me 1. For cell 0 is this is global index, this is a global one and this is a local one. 0 1 should essentially give me the global index, so that is 2, and similarly 0 2 should give me 3. So first I'll iterate to the cells, and for each cell I'll go through each of the phase, and for each phase if it is not a boundary phase then I'll do the summation of a and b times phi. And for boundary phases I don't have an a and b, but since the data structure is done in a way that each of these a and b is not equal to 0, so I'm just putting an if condition to take care of that. And then once I have done through all a and b, I'll just update the value of b. This is just an error term, and then the loop will just continue till your error is within your tolerance. So the Gauss ideal is again straightforward. The only thing that we haven't discussed here is how do you update your gradients. So to calculate the gradients, we would be needing the first thing is we actually require grad phi at f, and in order to calculate that, so see the notation is if this is phase f, we have cell 0 and cell 1. So I would be needing grad phi 0 and grad phi 1. To know grad phi 0, we are essentially using a gradient theorem where it is sigma phi f af by v0. So to determine this, first I would need to know phi f and af. So the first step is essentially to update the value of phi on all the phases. Since the value of phi is only stored at the cell centroids and not at phases, we are just taking an approximation that phi f is phi 0 plus phi 1 by 2. So this will introduce some error. So this is the first approximation. When the problem is when you have an boundary, in case of a boundary you don't have a cell 1, so you just take depending on your boundary condition. If you have a Neumann condition, your gradient is essentially 0, which means your value at the phase should be equal to value at the cell centroid. If it is a Dirichlet condition, you just take the Dirichlet value. If it is a mixed condition, then you have to appropriately take it. So if you have a mixed condition, if this is my phi 0, this is my phi boundary or phi phase, and this is my phi ambient. So like we have seen, phi 0 and boundary will be something in terms of a and b, and this will be something like 1 by h. So b equals phi f phase minus ambient, and this should give me phi 0 minus phi a, by I am just calling that as R equivalent. And from these equations you can actually determine the value of phi f. You just use this equation, you can get phi f in terms of phi 0 times some constant plus phi a some constant. So that is this particular expression here. So it will be some weight combination of phi 0 and weight average of phi 0 and phi ambient. So you will get a expression for phi f. So that will be used to once you know the value of phi f, the next step is you use a gradient theorem to calculate the cell gradients. So that is straightforward. You just take a summation of sigma phi f times af and then divide by that particular cell volume. This will give you the grad phi on that particular cell. So I will iterate through all the cells and update the gradients at all the cell centroids. The next step is to calculate the secondary gradient. Now that I know the cell gradients, so I've updated the gradient at phi as so like we have seen, we can either use an weighted average interpolation depending on the distance between the cell centroid and phase centroid, or in this particular case I've just taken the simple way of taking a mean of grad phi at the cell centroids instead of calculating the distances. So you can kind of use another interpolation where if this is cell 0 and cell 1, if this is my face, you can calculate this distance as d0f, d1f, and then to calculate grad phi at f can be taken as d1f times grad phi 1 plus d0f times grad phi 0 by d1f plus d0f. You can implement in this particular way as well. I've just taken a mean value, so it would be simpler to start with. In case of boundary, you don't have the value on gradient on the other one, so I've just taken the cells and C0 to be the value at the boundary. To get the secondary gradient, formula is again quite straightforward. So secondary gradient, like we are using, minus you have some factor, that is af dot af by af dot e zeta, and then you have a e psi dot e eta times d phi del phi del eta. This del phi del eta I am again approximating it as grad phi f, not approximating, del phi del eta is essentially grad phi dot e eta cap. This grad phi is essentially the current value of grad phi that is already stored in that particular mesh. So in the next iteration it will get updated. So ideally, since we do not know the value of phi, we cannot know the value of grad phi, but here we are using the previous iteration value. So this face dot grad essentially stores the previous iteration values. So you will just implement, you will just use the previous iteration. This is the default correction approach that we will be implementing here. So once you, so this is grad phi dot e eta times faces dot, so this entire factor is essentially your a and b term times E1 dot E eta. E1 is essentially E psi dot E eta, so that you will get your secondary gradient. So I put a minus here, where this is the default one. Now this is minus only for the cell 0. Now when we are dealing with the cell 1, it should be the other way around. So when you have your face, if these are my vertices, this is my E eta, if this is my E psi and this is my AF bar. If my E eta is already fixed, for a given phase I have already fixed my E eta and AF is already fixed, E psi will be, so if we are writing for cell 0, it will be positive. So the secondary gradient will be in this particular form. When you are writing for cell 1, then all these vectors are fixed, only that E psi will be reversed. Your AF will point in the opposite direction. So E eta should go in the other way. So instead of doing the calculation again, what we are just doing is instead of putting a minus here, we will, I think I have updated that in this part, where you update your coefficients. What we are trying to do is your face to cell of 0. 0 is essentially, so when you have a face, you have cell 0 and cell 1. So if this particular global index is equal to the current index that I am trying to search for, then I will just take the value of secondary gradient as it is. If not, then I will just instead of doing a plus, I will do a minus, so that the sign reversal will take place. Now that secondary gradient is also taken care of, so you first initialize your mesh and then you update your phase coefficient. This is not going to change from iteration to iteration for the particular problem we are trying to solve. If you have say SP term or something like this, is ensure that we have not we do not have any nonlinear source terms and all of that. So if you have nonlinear source terms, you need to kind of update this, you need to put this entire thing in another loop. So your nonlinear terms will essentially change your SC and SP, so you need to kind of put it in another loop. But here it is for like we do not have any source terms, so I have just taken one loop. There are Gauss-Seidel loop and this other loop. So this loop is for the secondary gradient terms. So instead of actually, so what the problem is, we need to find grad phi dot AF bar. So but instead of doing this, we were using grad phi dot E psi bar with some secondary gradient terms. So because of this approximation, we will not get a solution directly. that if the secondary gradient was used for the current problem you might get, but we are not using that, we are using from the previous iteration values. So grad phi dot f at the current iteration is essentially written in terms of this, where this is your previous iteration value. So since we are using a different value than the one that is supposed to be used, we put another loop so that at convergence when you have when your fees are essentially not changing, then this 0 and 1 will essentially be equal, and in that particular term your original equation, so your point of trying to replace phi with this plus some additional term will be satisfied only when convergence happens. So for that convergence we are keeping this additional loop. Now if you have a source term linearization, you will be having one more additional term, so you will be having one more loop. So and then you can also have your k as a function of temperature and all of that, then you need to take care of them, you need to linearize all of them and then put another loop. So as and when you make an approximation of the, it's like, why are we doing this is essentially again to retain our original linear form, so that our equations are still linear and we can use either Gauss-Seidel or say the TDMA or PDMA that we have discussed previously. Alternatively, if you want to use a current one, so instead of 0, say if you want to use the current value of phi, then in which case you need to know grad phi at the current time step, at the current iteration value, then the problem becomes non-linear and then you have to use some other method, say Newton-Raphson. If you want to use Newton-Raphson, then again you need to know your Hessian matrix, since which will again get complicated. So we will not go into that, maybe we will discuss that later. So I think the code is clear, or maybe I will pause for some time, so if you have any questions. Okay, there are no students.
Yeah, no questions actually.
Yeah, then maybe we can go through the implementation of it. So the code assumes that you are giving these vertices in a proper way. So how do I give input for that is, like we have seen, to calculate the volume I need to know the vertices in a predefined order in an anti-clockwise manner. So the indices are given in this way. So for this particular domain I will start with here. So first I start with cells, so I define my cells 0, 1, 2, 3. Once I define my cells, I would be needing faces and vertices as well. Each cell will be again given in terms of say if these are my cells, faces and vertices. Initially I will give some numbering to all of this, some labeling, so that it will be easy for us. So faces I can just label them. To feed in the information, we will be needing, we'll actually, okay, before going through the code, so we should finalize. So your vertices are essentially given as 0 to 7. So instead of giving this, we'll actually give the coordinates of each of these points. The x and y coordinates of each of these points will be stored in my vertices. Faces is essentially indication of my vertices. So the first we will start with the cells. So your cells should, in terms of vertices, if I were to denote in terms of vertices, cell 0 should be written as 0, 1, 8 and 7. Similarly, cell 1 is written in terms of 1. So cell 0 is written in this way, so in the anti-clockwise fashion. Cell 1 again will go in the anti-clockwise fashion, so it will be 1, 2, 3 and 8. So similarly you will do for the other two cells. Once I have defined cell in terms of vertices, I can define in terms of faces as well. So if I were to do in terms of faces, it will go in the anti-clockwise fashion. So it will be 0, 8, 11, 7, or similarly if I do it for this, it will be 1, 2, 9 and 8. You can write for the other cells as well, for the other two cells. It's like if you want to write for this, it will be 9, 3, 4 and 10. This will be 11, 10, 5 and 6. So this is straightforward. And for faces, we will determine in terms of vertices. So this is for say for face 0, it will be 0 and 1. For face 1, it will be 1 and 2. Similarly, you will go on for all the faces. Now once I define the faces and cells, the next step is to give your boundaries. So like we have seen here, we have 20 this the boundary conditions. So for a Dirichlet condition, we have on phase 0, phase 1, 2 and 3 don't have any boundary condition, 4 and 5 will again be 0, 6 and 7 will be again 30, 30, that is the Dirichlet condition. Here since we do not have any flux anywhere, so it is 0 everywhere, and it will be similar for both your H and phi terms, since we don't have any mixed boundary conditions. So you have given the boundary conditions, and then you also specified your cells. So this gives your input to your code. The next step is to essentially get your connectivity matrices. Like in this, there is a helper function to solve for that. So just to give you an idea of how the connectivity matrix looks, say suppose phase 2 cell. Phase 2 cell connectivity matrix, what it does is, say you consider phase 8 and cell 0. Phase 8 has two cells, 0 and 1 as its neighbors. So one of them will be 0 and the other one will essentially be 1. So what phase 2 cell is, takes a global phase index and then a local cell index and then maps it to a global cell index. Cell to phase is slightly so we haven't seen cell to phase, so maybe we'll go through that. Where we use cell to phase is update coefficients. So this is where I needed the inverse mapping. So when you are going through for a given cell, each cell is surrounded by certain phases. So when you know the global index of the cell and the data structure is chosen in such a way that each cell stores the index of the phase, so you know the global phase index as well, but you don't know the corresponding okay, this is something that is used. So I've used the data structure in such a way that the cell stores the index of the phase instead of the phase value as directly, so that you can directly know the phase index of it. What I mean to say is just so if this is cell 0, this is a phase. Instead of defining as 0, 1 and 2 as my local phases, what I have done is store the cell data structure in such a way it stores the global phase index. Instead of storing 0, it will store the global phase value. So you can directly use the index to get your phase index, use the array index to get your phase index. That makes your things straightforward later. If we are using a cell based data structure instead of a phase based data structure, then it will be different. Then you would be needing the inverse mapping that we haven't anyway used in this particular case. So if you are using a cell based structure, then you would be needing another matrix, cell to phase, in a similar manner like this. The reason why we didn't use this is because if you are to using a cell based data structure, then you need to evaluate your like you will be iterating through your phases and you will be iterating through your cells, and then for each cell you need to calculate fluxes in all the phases, and then for the neighboring cell again you will calculate the flux. So you will be actually doing the same calculation twice. So instead of cell based one, we have chosen phase based one. Yeah, now that we have the code, the next important point is essentially to know test this on various cases. So I haven't so in our particular problems, I have just taken 2 cases and like essentially 4 cases, 2 cases from the last week's sessions and 2 cases from this week. So one case is essentially the parallelogram where you have a quadrilateral mesh. So this is a non-orthogonal mesh. And then I have taken another grid where you have all types of boundary conditions. So you have a Dirichlet condition, a Neumann condition, and then you have a mixed boundary condition. This is one test case that you can try your code on. And then there are other possibilities where you have your source, like in this particular case I have just assumed a constant source term. Now you can have a temperature dependent source term, that is another test case. So I have considered 4 test cases. So first one is an non-orthogonal, first we will start with the simple ones. So we will take an orthogonal orthogonal mesh, but with all kinds of boundary conditions. Second, we will consider a non-orthogonal mesh. With a few boundary conditions, but both of these have either, so SP is essentially 0. The next level of complexity you can add to this is just take the two more combinations. You consider an orthogonal mesh and then you put SP not equal to 0, and then the next complexity will be put a non-orthogonal term and then put SP not equal to 0. So that will add one level of complexity. In both of these cases you can consider a mixed kind of boundary condition. So instead of a Dirichlet condition, you can use a mixed boundary condition. So that will be the added level. So I have tested the code on this 4 of this. So we will consider each problem one by one and see how it turns out. Now coming to the implementation aspects before actually going into the code. Implementation wise, your secondary gradient sometimes can lead to, like, what we are trying to do is when we instead of using grad phi.af, we are essentially replacing this with at the current time step plus at the previous time step, previous iteration value. So because of this, since it is not an actual one, you are changing your path to the final solution. Sometimes it could lead to divergence. So it is preferred to use an under relaxation. So where do you use under relaxation? So in your Gauss Seidel, which I have not done here, but when you are actually trying to, if you find that your solution is diverging, then in this particular step where you are actually updating phi in terms of this temp is essentially a variable that will store the value of so temp is essentially a variable that stores sigma a and b phi and b plus b by ap. So here I have just updated the current value of phi to be this particular temp, which will, if this is found to be diverging, then you can just use some kind of relaxation where you won't update completely. You will use the previous value. If the previous value is say this phi, you use phi star times some factor to 1 minus a times this temp. So what I am trying to do is whatever information I get from the current iteration, I will not use it completely to update the value of phi. Instead I will use only a partial information of this, and I will use the previous information. So this is just to ensure that you have a proper convergence, and it maybe in this particular simple cases is not a big problem, but when you have more kind of a skewness in your mesh, in your say in case of non-orthogonal meshes where skewness is essentially, what I mean by skewness is say you have something like so where, or you can say convex, or where your cell centroid might not lie in your cell. So yeah, I can say put a straightforward problem here. So in the way that we implemented, say if suppose you have a cell like this, the indices, I have the vertices, coordinates of all these vertices, and if I just do an average of them, if it so happens that your cell centroid falls somewhere here outside of the particular cell that you are trying to solve. So in this particular case, the way we formulated it, if you were to calculate for this phase, your outward normal should be in this direction, but the way the code is implemented will try to put it in a different direction, so your terms will not be properly done. So this might lead to some other issues. So you need to have a proper mesh, like to prevent elements like this. We are not dealing with mesh anyway here. So the only thing I want to highlight is you need to implement some kind of a relaxation scheme so that you will not lead to some divergence, so that your solution won't be diverged. So we will see all the 4 problems one by one. So the first problem is taken from the previous class. So this is the mesh I have tried on. So here you have a source term of 1 minus t. So you have SC as well as SP term, and it is an equilateral. All triangles are equilateral, so it is a non-orthogonal mesh. So this is the first problem that we will be solving. So the boundary conditions are all mixed conditions where you have h equal to 1 and phi ambient is considered to be 0. The second problem is the same domain, but instead of using a triangle, I used a quadrilateral element here. So you have a non-orthogonality because of this. So this same boundary conditions, it will be solved on this. The same code will be used on this. And the next two cases are one is this parallelogram with Dirichlet as well as Neumann conditions, and then you have consider this is all are equilateral triangles. So this is again a non-orthogonal mesh with all kinds of boundary conditions. We will see one by one. We just go through the code. So the code that we discussed previously is again I just put it in one header file, so we will not go through this, like we already went through this. So the inputs are essentially the vertices that you will be giving, the coordinate points of all the vertices. The next is the connectivity between the faces, how this essentially stores these indices here essentially denote the array of this. So if it is 0 1, it means it is 0 0 this first one and the second one. So this is a face between these two vertices. In a similar way, you will define for all the faces cells, and in terms of faces as well as in terms of vertices. You initialize your mesh, you add the vertices, you add faces, you add cells, and then you update your connectivity. Once you have your mesh, the next step is to essentially give your boundary conditions. So I've just given the boundary conditions. In the first problem, the boundary conditions are essentially mixed conditions with h equal to 1 and phi equal to 0. Since we don't have any Dirichlet and Neumann condition, I've just put zeros everywhere. After adding the boundaries, you just take an initial guess of phi everywhere, which I'm just considering 1, and then you initialize your mesh, then you update your phase so this is, you can just call the solve off so that it solves. So what it does is essentially you initialize your mesh, and then it will update your phase coefficients, and then it will update your it will essentially formulate your cell equations and then solve them using Gauss-Seidel method. So how do we test it? The obvious thing is to just try for different various boundary so you can try for various initial guesses of phi and see if the code is essentially giving you the same value of phi every time you run with different. Say I've just started with an initial guess of 1 everywhere in the domain. You can try giving different guesses, say 0 or some other values, and then see if it is converging to the same value. That could be one what you can say a sanity check or something to see if your code is working. So this again is straightforward. So the only thing you need to care about is how you give your inputs for this code. Maybe I'll go through the solution. It doesn't make that much sense here, but these values you can compare with the previous week solutions that we have derived with hand calculation. So this matches with our hand calculation results. There were some errors in our hand calculation where we kind of I've kind of calculated the centroid incorrectly. So this is something that you get if you make that corrections. And the second problem, in the last week we tried solving it using symbolic to get these equations. So the way we implemented this is we already discretized the equations with hand, and we know what is A and B and all of that. Instead of doing in that way, what we can do alternatively is use some symbolic methods, if you are familiar with some symbolic methods, to actually discretize your cells automatically, so that you can automate your discretizing process. So in this way you don't have to write your equations in a particular way. Say I have defined what is my A, I have defined what is my AFR and all of that. Instead of doing that, you can actually use symbolic to generate your own equations and then discretize your cells. So the second problem is again similar to the previous one. The only difference is instead of having all equilateral triangles, I had a quadrilateral in between. So I just had one more additional face. So now we will be having 10 faces, and then you have 4 cells, 0 1 2 3. The first cell has 4 faces, that is my quadrilateral element, and the remaining have 3 faces each. So those are my triangular equilateral, one is equilateral triangle and the other 2 are some right angle triangles. The remaining steps are again straightforward. boundary conditions are also straightforward. So if you solve this again, you will get a different solution. So the question is, there was a question last week where the student was asking about the accuracy of this method. So if you were to deal with an unstructured mesh, and then would you get the same result if you use a structured mesh? So as we have seen, at convergence, your secondary gradient term should ideally be equal to the original flux. So it shouldn't give you any differences in that. And the way is when the advantage with this unstructured meshes is only when you have complex geometries, it would be easy to mesh those things, which is not possible with your structured meshes. In this particular case, say even for the triangular domain that we are considering, if you use a Cartesian mesh of at right angles to each other, you would end up with some regions of the geometry being left out. That would lead to some inaccuracies if your problem is sensitive to your geometry. So that is something that is being eliminated using an unstructured mesh. So I've just printed the cell equations. So this is my AP term, and then this is sigma NB. The first cell is actually quadrilateral element, so you have 4 coefficients. In the quadrilateral, you have the bottom face to be a boundary, so you don't have the first coefficient, and then you have the remaining 2 coefficients. So the thing to notice here, you have some symmetry also associated with it, so you have 2 similar equations, which when we were doing hand calculations, we kind of eliminated it directly by saying since it is a symmetric element, we don't have to solve for all of them, so we just solve for one equation and then we used it for all other cells, which is not the case here. Okay, so we will keep that aside. Maybe there is some, in the previous case when we were calculating the volume, it is assumed that the vertices are given in phase center way, so we can give me a second, I think there should be a minus here. So maybe I will just go through this later. So there might be some bug in this. So you shouldn't actually get a minus term here. Or you might end up getting a minus term because of your secondary gradient. Yeah, because of secondary gradient, you might end up getting a minus sign as well. This is for the parallelogram problem that we are solving. In the parallelogram problem, you first specify the vertices in anticlockwise fashion, and then you specify each of the faces in anticlockwise, and then you give your cells. So the boundary conditions, again as we have seen, you have the bottom 2 faces as a Dirichlet condition and the left border as again Dirichlet conditions. The flux are all other boundary conditions are 0. So this is, so I think the implementation is now straightforward. The only thing that you need to care about is this particular portion, how you specify your coordinates, which is something is taken care of automatically by mesh generation algorithms, which we are not discussing in this particular course. Maybe I can run these things to show the output, but if you have any doubts, then we can go through them. I've just, so these are my equations for that particular, the last problem. When we have an equilateral triangle, it is not symmetrical, so you might have different values of AP and A and B here. So when you have 2 boundaries, you just have 2 of the coefficients to be 0. So, and the other one, this is the interior cell where you do not have any boundaries, so you have all the 3 coefficients, and the other 3 cells have 2 boundaries, so 2 of the coefficients to be 0, and you have a third coefficient. And these are the final solutions. So in the final solution, you can check the cell towards the east one is essentially, so if you see, so if you see in these cells, so cells 3 and 4 are closer to this particular boundary, so you expect to have them a higher value of phi, and 2 and 3 and are essentially closer to the Dirichlet condition, and this is a flux. So you can see the terms to be closer to 1. So 3 and 4 are essentially the last ones, have very high values because of the Dirichlet condition, and then these are the adiabatic ones, and this is the center cell. And then for question 2, if you see these cells, these are two Dirichlet conditions. So you expect to have a higher temperature at so this is an adiabatic condition. The upper tip is an adiabatic one, and the right one is also an adiabatic one. So you expect to have a higher temperatures on the top ones and some intermediate temperature here. So if you just see the values, it's like it's in the similar pattern. What this pattern tells you is your heat flows in some direction like this. So it will flow from here to here, here to here, and in this particular way. So I've just done, I have not completely seen till convergence. So just ask you to do for 4 iterations or 5 iterations and then see the values of them. I think that pretty much. Okay, we have around 10 minutes left. Yeah, if you have any questions, then we can discuss, or maybe we can take up another problem. Yeah, we have around 10 minutes left. If you have any questions, then we can take it up.
Yeah, I'm good.
Yeah, good. Okay, then the next question I was trying to discuss is essentially the old problem that we visited previously. You just take 2 parallel plates, and then you have, since convection has already started, so the first equation is straightforward. So you have
Yeah, actually, I can ask one question, because
Okay.
we're discussing non-orthogonal kind of things.
Okay.
So did we discuss anything like adaptive? Because I think we can.
No.
Adaptive.
Oh, okay. I haven't added,
Adapt-
but I can. Okay.
Yeah, changing with time, just that cells change their sizes with different locations.
So you're saying as through iterate your cells should be changing, or before the
No.
solving process?
Just the mesh, it's like big cells on, like if you take 2 parallel plates and you take a circle, like flow past the cylinder.
Okay.
Yeah. So we know that behind the cylinder, the flow is vortex, and depending on the Reynolds number, you need to have a lot of cells at some areas and not any. Did we discuss this? I
No.
was just wondering.
No.
If we had adaptive, I was just wondering, like, how much difference would that make, in terms of implementation and.
Okay. So okay, but that would
Related to-
essentially be that would essentially be into the meshing. So
Mesh process.
Yeah.
Okay.
so we are just focusing on the method part of it. So if you are given a mesh, how do you go ahead and solve it?
Okay, so if the adaptive mesh is like orthogonal, non-orthogonal, then all this part comes, like
Yeah.
circle and.
Yes. So but the general implementation is when you just take the dot product, it takes care of everything. So you don't have to worry much about it. Yeah. So the problem I was trying to point is when you have 2 parallel plate, the one we discussed previously. So in a fully developed design, you have okay, u is just a function of y. So u times du dy is essentially minus dp dx. Okay, there will be a rho term, something like this, and then you also have temperature equation that we considered previously. So you have a rho Cp times say steady process u times delta del x, and we don't have a v term, plus k times del square t del x square del square t del y square, and then we have so this is your viscous dissipation term. So when we were discussing this previously, we assumed that del t del x is essentially equal to 0, and then we solved this problem. But then at that time we also raised a point that del t del x is not essentially 0 always. So when you have different kind of boundary conditions, your temperature will essentially change as a function of x. even when it is fully developed, even it is hydrodynamically fully developed, your temperature can change as a function of x. So now that we are familiar with how to deal with in 2D, so we can solve this problem. So since we know the solution of u, we just have 10 minutes, so maybe I'll just outline the process and then we'll take it up in the next class. So we know the profile of u as something like this. This is h, this is my x-axis and this is my y. Since we know the value of u, you just have to solve this. So to compare with our standard form of equation, there are two ways you can form this. You can either use it as a convective diffusion one, since you have u term here. So if you compare with your standard form, it is something like some del dot rho u phi. So it's for a steady process plus some source term. So if you compare this form, so this is your k term and this is your this particular term here. So we can solve it as a convective diffusion problem, convection plus diffusion or advection plus diffusion, or since it is your velocity and your energy equation are essentially not coupled to each other. In this particular case, you actually know the velocity profile ahead of time, so you can directly use this expression here, and which will kind of simplify your problem. So if you use that, in that particular case again, you will be left out with expression like will be k times del square t plus you have, you know, this analytical expression for this, so you can just substitute that and get this value times rho Cp del T del x. Now you can consider this entire term to be your source term and this is your diffusion term and solve this equation. The only problem here is or maybe the advantage here is you do not know the del T del x ahead of time, since like t is an unknown, you do not know this. So here again we can use a similar concept that we are using for secondary gradient. So to calculate, say when we are using an unstructured mesh, or even we already have the value of grad t evaluated at the previous iteration step, so you just take the grad t dot I hat, so this will give you del T del x and you can use this, and since at your final step you actually after it is converged, it will actually be solving the original equation, but to use your Gauss seidel you can use this grad t that you evaluated for your unstructured mesh to solve this term. This is again useful even when you are dealing with turbulent viscosity where you have your velocity gradients to be done. So the gradient term can be used in cases like this in addition to doing for the secondary gradient calculation. That is the only point I would like to bring here. So like it's just 7 minutes, so instead of taking the we'll take up the problem in the next session and actually solve and compare the value in the two cases. So it will anyway be similar, so you can just see how iteration gets through convergence. Then we will find out that temperature here, though it is not a function like previously when we kind of assumed del T del x equal to 0. So now we will see when we try to solve this if this assumption is actually true or not. If not, then how do we deal with that? That is something that maybe we will take up in the next session. We just have 5 minutes left. I think we are good to go. Thank you all for joining.